Hello, everyone. So I'm Roseline Polle. I'm a data scientist at Holistic AI. We are an AI risk management company, and today I want to talk about bias in machine learning. So I'll first go through what machine learning is and give some example of application and biased applications. Then I'll define what bias is and where it comes from, and finally how we can measure and mitigate for it. So what is machine learning? Machine learning refers to algorithms that can learn from data and improve over time without being explicitly programmed. So there's a big emphasis on data in machine learning that we learn from, that the algorithm learns from, and then it applies what it's learned to new unseen real-life data. We also often talk about machine learning algorithms as black boxes, which take an input, then an algorithm is run, and it just gives some output. The output could be very different forms. It could be binary, 0, 1. It could be a score. It could be generated images, etc. And why do we use machine learning and where? Why? Because it's good at doing tasks that humans are not so great at doing, like finding patterns in large data sets, finding correlation between these data, also predictive analysis, and also automate some tasks. And where do we use it? So basically everywhere, but some examples are in healthcare, for weather forecasting, to automate self-driving car, or in recruitment to go through many, many different CVs, etc. But the problem is, among other problems, machine learning can be biased. And I'll define what bias is in a minute and where it comes from, but first I want to give some example of application, real-life application that were biased. The first one is a recruitment algorithm by Amazon, which was biased against women. Fortunately, it was scrapped before real use, so it never saw the light. But what happened is that the algorithm would go through CV and discriminate against the word woman. So every time it would see the word woman in a CV, it would classify that candidate as less qualified for the job. Another example is in gender recognition. There is this famous study published by MIT called Gender Shades, where the researcher assessed 3 different gender classification algorithms. And they noticed that for black women, there was up to 35% error rate. And for white men, this error rate was only up to 1%. So there's a massive difference in performances here. So now, what is bias and where does it come from? So bias, the global definition, it's a tendency to favor one group or idea over others, and it can be based on a person's race, gender, religion, etc. In machine learning, it translates to systematic errors that are made in the decision-making process of an algorithm that lead to inaccurate or unfair outcomes. For instance, the systematic decision to correlate the fact that there's a word woman in a CV with the fact that the candidate is less qualified. And to understand where it comes from, I first want to show a quick life cycle of how machine learning works. So it starts with the world that we live in. And what we do is we sample some population that we want to apply train the machine learning model on from that world. And then we take some measurement from that population to create our data sets. The measurement could be, for instance, taking a picture of someone for a facial recognition algorithm, or it could just be making people fill a form with some data about themselves, etc. And that creates some data set. There's different type of data set. There's the one that we create to train and test the model. There's some data set used to benchmark models. And then there's a data set that we use the model in real time, in real life for. And all this data goes through the model and give an output. So the model is the black box that I was talking about earlier. So now where does bias creep in that process? First, we have historical bias, when bias is already present in the world, and it doesn't matter how you do the process after, it just is there already. And that was the case for the Amazon recruitment algorithm. The reason why it was biased is because it was trained on historical data where mostly male candidates were successful. Then we have sampling bias, and sampling bias is the way we select the population that we're going to train the model on. An example is, for instance, if we train an algorithm to recognize wedding pictures and we give it data from Europe or the US, it will correlate a white dress with a wedding picture. But there is some countries like India, Pakistan, or China where the wedding dress is not white, it's going to be red, for instance. So there would be a bias against these pictures if you train it wrongly. Then we can have a measurement bias. Measurement bias occurs when we measure differently different group of the population. An example is if we have an individual living in a neighborhood with a high police presence, like they would be arrested more than an individual with the same crime history with not such a high police presence. And if we use that the number of arrests in an algorithm, it will then lead further away to bias in the way in that algorithm. And all these type of bias that I talked about are reflected in the data set, but we can also have bias in, for instance, the way we choose the model. So aggregation bias is when we choose one model to model something that would normally require two models for different groups of a population. And a typical example is how we measure diabetes in different ethnicities. So there's different biomarkers for different ethnicities. So in theory, it requires two models. And if we were to use one model, we would introduce a bias. So now how do we measure bias? So in this presentation, I'm just going to constrain myself to a binary classification task in machine learning, which means we have a binary output to the algorithm, so 0 or 1. And more specifically, I'm going to go through a CV selection example where a candidate is either pass or fail. So to measure bias, we first need to choose which concept of fairness applies to our use case. So there's two concepts of fairness that exist in the fair machine learning world today. There's equality of outcome and equality of opportunity. For equality of outcome, we care about the outcome and not so much about how the selection process works. We want the same proportion of successful candidates for each group. So for instance, if we have 10 female and 100 male going through a selection process, a perfectly fair outcome would be 3 female and 30 male being selected. For equality of opportunity, we don't care so much about the outcome, but we care about the selection process. We want it to have similar model performance, like accuracy, recall, precision, for all the different groups. So now I'll give some example of how we can measure. So for equality of outcome, the most common metric is called disparate impact. And it simply compares with a ratio the different selection rates of the different group. So here we have a selection rate of 30% for men and 20% for women. So the selection rate of men is 50% higher than women. And the disparate impact would be just the ratio of the two, with the selection rate of the disadvantaged group, here women, on top. And it's going to be 0.67. A rule of thumb says that it should be above 0.8. That's quite an arbitrary number, but it's very well established in the community, in recruitment especially, and it's in some US law text as well. For equality of opportunity, the example I'm going to take is the equalized odds. So equalized odds mean that we want the true positive rate, also called the recall, and the false positive rate to be the same. So basically, here we have an example where we have a black person that should pass, meaning that in the training algorithm they're labeled, so for training they should pass. But the algorithm predict them as pass 78% of the time if we take a random black person. So correctly predict them as pass. And then we have a white person that should pass, and the algorithm correctly predict them as pass 95% of the time. So we can see the white person is advantage here. And the false positive rate is the same, but in the opposite. So like the black person and the white person, they both should fail. The black person is predicted as pass 2% of the time, whereas the white person is predicted as pass 10% of the time. So we also have a discrepancy here, and the goal of equalized odds is to bridge that gap and get the same proportion for everyone. Now, how can we mitigate for bias, still in a binary classification context? So generally, for the techniques to mitigate for bias will be classified into pre-processing, where they modify the data before we train the model, in processing, and it's affecting basically the training process to remove bias, or post-processing, where we change the outcome directly. The first method I'm going to present is a pre-processing method, and it's called reweighting. And it weights the example in each group label combination so we can rebalance the data set that we trained the model on. So for instance, if we have the selected candidates, we have 5 men and 2 women in our training examples, we want to give more weights to the 2 women so that the model will be penalized more for the errors that it makes on the women. And that will improve the training and therefore the selection process itself and equality of opportunity. The second method is an in-processing method, and it's called prejudice remover. And it adds a discrimination-aware regularization term to the learning objective. So in machine learning, when we train a model, we, in effect, minimize a loss, so minimize an objective function. And generally, that loss would be just the error that the algorithm makes in the training process. But we will add here a term that accounts for bias and help us do a trade-off between the error and the bias. And that can improve both equality of opportunity or outcome, depending on which regularization term we use. So now I've talked about binary classification, and in most contexts you'll see people talk about binary classification when they talk about bias, but there's many other tasks, and often real-life application won't be binary classification. So I just want to open a bit on what else there can be. So some other tasks that we can have in machine learning is multi-class classification. For instance, an individual that gets classified at low, medium, or high risk in an insurance context. Then we can have regression tasks. For instance, if someone is given a credit score, clustering, where different clients get segmented in different clusters and get offered different products, and recommender systems, so for instance, getting recommended in a hotel or a song, etc. So in all these tasks, there will be different metrics and ways of measuring for bias, and they will come up in different ways, and you can apply different mitigation techniques. So I don't have time to go through that, but I suggest that if you're interested by the subject, Holistic AI, people at Holistic AI, and also some partners, we created 2 courses for the Turing Institute. And the first one is about in a binary classification context and also a more general context, so presenting bias in a also philosophical way, etc. And the second one goes beyond binary classification and presents the way you can measure and mitigate in the different tasks that I just talked about. So thank you for attending the presentation. If you have questions, I don't know if we have time now, and if not, you can also contact me on this email.